Okay. Hello. Are we live? Let's check. Okay, we are live. Fine. Hello everyone. This is my first attempt at streaming or YouTubing or whatever you want to call. Although this is a personal project of mine where I would like to solve some questions and explain it to others in the process. But let's see where this goes. For the first stream, we will be trying to solve some questions from the chapter Atomic Structure. It is a significant part of the chemistry syllabus in JEE Mains and is usually considered one of the chapters which does not requires too much effort but is of significant weightage. I shall be trying to solve some questions from my coaching module. I have tried to solve some questions before and I've gotten through some of them. I am currently solving questions from the spectrum part of the chapter. As far as the stream is concerned, I will not do it for more than 20 minutes for now because this is the first stream, and once I get the hang of it, we'll try to extend the hours. But for now, let's start with what we can. I'll be using ChatGPT for the solutions and to understand the explanation of each question because I'm not having a very reliable source and I don't have too much time to go through every single question and spend my time. Ideally, that should be done, but I cannot spend so much time on every single question. So for first, we will have a look if we can solve the questions well and good, or else we'll refer to ChatGPT for some explanation. All right. So if you can see on the screen right now, we'll be solving the 35th question, which is the shortest wavelength lambda for the Lyman series of hydrogen atom is, and they have given the Rydberg's constant for hydrogen, which is 109678 centimeter inverse with 4 options given below. Okay, now if I were to apply my brain for this question, I know that Lyman series, Lyman, Balmer, Paschen, so these are the first 3 series, and the Lyman series being the first one has hydrogen spectra or the spectral lines that end at the second what can we say, energy level, when the electrons go from a higher level, be it 3, 4, 5, infinity, and end at the second energy level. That is Lyman, if I'm not wrong, or is it the first one? Let me just check the module. Okay, according to the module, yeah, Lyman is the one which ends at the first energy level. So first energy level, and we are supposed to find the shortest wavelength, shortest lambda. Okay, if I were to apply my brain, so the concept goes, electrons fall from a higher energy state to a lower energy state, or the ground state, and in this case it's the first energy state since we're talking about Lyman. And once they are in the process of falling down from a higher energy state, they release some sort of light, so that has certain frequency and wavelength. So now when one electron is falling from a higher level, they're asking us to find this specific wavelength where it will be the shortest. Now immediately that is a concept that comes in my head, but there is no formula as such or anywhere where I can start the question from. The closest I can think is that the higher the energy level, the higher the wavelength, because when you are falling from a higher level, you're going to release more light, so that's going to give more wavelength. I think that's what the answer is, but I generally have no idea how to proceed with the question. So we'll be looking at the solution and trying to make of what they have given. Okay. For the Lyman series, the shortest wavelength corresponds to the transition from n is equal to infinity to n is equal to 1. Okay, so the n is equal to 1 part is correct, but n is equal to infinity, I'm not sure why they have done that. I'm assuming because, see, I know that frequency is directly proportional to the energy that is emitted by a photon or an electron in this case, and the higher the frequency, the higher the energy. So there is this relation between energy of a photon and energy of the wavelength and frequency of the photon. So the best way to understand is when you see that the 5G spectrum for telephones, when they are supposed to transmit over a large distance, they have a very large wavelength, as in they spread over a large span in one short area. Because of that, they have a poor strength, which means they cannot pierce through different walls or thicker walls, but they can travel for a very far distance. So the longer wavelength, the lower the energy. But here they are asking us to find the shortest wavelength, which means the wavelength is short and the frequency is high, because since wavelength is short, in one certain amount of area there is a lot of waves getting reciprocated. So at this point I'm genuinely not sure what that concept is supposed to mean. I think I'll have to ask ChatGPT for an explanation. But okay, for now let's just assume that n is equal to infinity to 1 gives us the shortest wavelength. Then they have used the wave number formula, which I have doubt in, because the wave number formula which I remember was given by, if I'm not wrong, Rydberg himself, and he had a constant RH obviously multiplied by z square into 1 upon n1 square minus 1 upon n2 square, when n1 and n2 are the energy states, n1 being the final one where the electron finally comes, and n2 is the one that comes initially from. But here they have seemed to use some different formula, so let's just check where they have used that. Yeah, see, this wavelength formula is rz square times 1 upon n1 square minus 1 upon n2 square. And over here, okay, this makes sense. Okay, now I get. Okay, they have used the same formula. They have just taken z as h, so it has become 1, and 1 upon 1 upon infinity square is an indefinite form, or we can say 0. So 1 minus 0. So RH times 1 becomes RH. So that's the wave number for this specific light that has come out from the Lyman series. So now, since we know that wave number is inverse of a wavelength, we can inverse this value which you have found, that is 1 upon RH, and we should get the lambda for that light. Okay, that makes sense. The only part that does not make sense is why they have taken it from n is equal to infinity to n is equal to 1. So I think I've asked this question already to ChatGPT. Okay, this is a different. Not this. Okay, let's ask it. What is my doubt exactly? My doubt is, why did we have to go from infinity to 1 to find the shortest wavelength in question number 5? Why did we go from infinity to 1 to find the shortest wavelength in question number 35? Infinity. Okay, let's see what response ChatGPT comes up with. I hope the audio is clear and everybody can hear it. Everybody being me, because I don't think there are any viewers as of now. Okay, wavelength and energy relationship. Yeah, this is what I was talking about. The energy difference delta E between two levels determines wavelength lambda of the emitted photon, according to the formula, which is E equal to hc upon lambda. A larger energy difference corresponds to a shorter wavelength. Okay, so you're telling me ki delta E is equal to hc upon lambda. Okay, hc upon lambda means energy is inversely proportional to the wavelength. So if the wavelength increases, then the energy difference between those two energy states reduces. Okay, what am I supposed to do with that information? Series limit, shortest wavelength. In any spectral series, the shortest wavelength corresponds to the largest possible energy transition in that series. Okay, yeah, makes sense. If the lambda is very small, shortest wavelength, then the energy gap will be very high. Okay, and what have they asked here? They have asked to find the shortest wavelength. Okay, so if you want me to find the shortest wavelength, then you're basically asking me to find the largest energy difference. Yeah, that I think makes a little more sense. For the Lyman series, all transitions end at 1. The largest possible energy transition from Lyman series. Okay. So instead of just looking at the question at face value, okay, this is something interesting I've learned. If you're looking at a question, don't just look at its face value. In fact, try to relate some different concept that is given in the question, because in the question they have spoken just about wavelength, but with that we can't really do much to find what is the shortest or the longest wavelength. That is a difficult thing to find. I don't know, maybe with enough research or with data you can find that, but as in at this JE level we know that there is an energy relation with the this one wavelength. So we can use the concept of energy because that is easier to understand. Because of this formula E is equal to hc upon lambda, we know that energy is inversely proportional to the wavelength. If they're asking us to find the shortest wavelength, they're basically, in another word or paraphrasing the same question, they're asking us to find the largest energy gap difference. And in a Lyman series where everything ends at 1, the largest gap is always obviously found from infinity to 1. So what they're asking us to find is the wavelength of the Lyman transition from infinity to 1. That's what they've asked. So such a short, like it's a really short question, one line question just printed on the paper, but when you look at it, it actually has a huge meaning behind it. So what we're basically supposed to find is the largest energy gap, which is from infinity to 1. Okay. Delta E for Lyman is, so this is some other question. Series limit is infinity to 1, so it makes sense. Why n infinity? Because the series is the shortest wavelength. Makes sense. When an electron moves from n is equal to infinity, where energy is 0, the energy difference is infinity minus energy in the first state. So infinity by energy is 0 minus energy at first orbit. Okay, I remember this formula, but I'm not able to recall exactly. I think it is something to do with minus 13.6 upon into z square upon n square, where z is the atomic number. So here it's 1, and upon 1 square. Let me just double check. I'll have to recall formulas like this. I'm generally not the best at remembering all formulas at one go. I have to revise them multiple times to gulp them inside my mind. Energy equal to hc by lambda. Yeah, total energy is minus 13.6 times z square upon n square. So that is where they have taken 1 square from, and from that you get a change in entire energy state is 13.6 electron volt. Okay, this is the maximum possible energy difference in the Lyman series, and thus it produces the shortest possible wavelength. Okay, now the question here is in angstrom. Okay, so ChatGPT has given us an example, but to solve the question it is slightly easier. So we need to know this concept before solving this question, but to solve this exact question we can use basic question 35. They've given us the Rydberg's constant for hydrogen 109678 centimeter inverse, and they've asked us to find the shortest wavelength, which is the largest energy gap. Now the largest energy gap is from infinity to n equals 1. Where am I supposed to find? Yeah, wave number. Wave number is r times z square into 1 upon n 1 square minus 1 upon n 2 square. So r h is given, which is this value. Z square is 1 because we're talking about hydrogen, and 1 is the final state. So for Lyman it is 1, so this entire thing becomes 1, and n initial which is n 2 square is infinity, so 1 upon infinity square is 0, because and RH times 1. So we are supposed to find wave number equals to RH. Now this corresponds to the inverse of a wavelength, so we can inverse this value also to find the wavelength. So 1 upon RH. Now 1 upon RH is 109678 centimeter inverse, so that is our wavelength. But now the answer is in angstrom, and we have the centimeter inverse value of the wavelength. Now how am I supposed to convert centimeter inverse to angstrom? As far as I remember, I have not come across any conversions. The closest I have gotten is 1 nanometer equals to 10 angstrom. If I'm not wrong, 1 nanometer is 1 times 10 raised to minus 6 meters. But I'm not sure how to solve this. Let's see if we can. Okay, 35. Okay, so they have not given any calculation. They have instantly just written down 911.7 angstrom. Can you show me how did you convert 1 divided by 109,678 centimeter inverse to angstrom? Okay, apparently they want my feedback. Convert 10 this. We need to understand the value. This value represents the wavelength of a reciprocal in centimeters. Okay, it's still calculating everything. Wavelength in reciprocal centimeters, also known as wave number. Okay, reciprocal of this wave number will give us the wavelength in centimeters. Acha, so the inverse that I've gotten is not centimeter inverse, it's centimeter. Makes sense. Which we can then convert to angstroms. 1 centimeter equals to 10 raised to 8 angstrom. Okay, this I did not know. I think I should note that down. I know that 1 nanometer is 10 raised to 9 angstrom, minus 9 angstrom. Sorry, just 10 angstrom. Okay. And 1 meter equals to centimeter. Centimeter equals to 10 raised to 8 angstrom. So if I just multiply this with 10, I should, so 10 raised to 8, I should get the answer in angstrom. That's what they're asking me to do. But then how am I supposed to find out this value, because I won't have a calculator in my examination hall. So 10 raised to 8 upon 109678. Okay. First of all, let's give him this feedback which he was asking for to understand . Okay, convert the wavelength in angstrom. This answer is more precise, I think. I mean, I got understood in one go, so I think I would prefer this. I did not read that, but this is straight enough to understand. But my second question is, how do I calculate 10 raised to 8 divided by 109678 without a calculator? This is a part in chemistry. Even this is not physical chemistry, I think this is inorganic. Physical chemistry has such weird calculations which I am not really fluent with, and the problem is this kind of questions are very prominent in exams like MHT CET, where it is, they don't have any negative marking, it's all positive marks, one mark for each question, but you have such a huge number of questions and all of them are very easy but have a lot of calculative questions, so they might take time. So there you have to be fast. So we have to learn these tricks. What they have done here is estimate the value, starting by estimating this to, okay, they just estimated the value, which is close and easier to work with. Now calculate, we can break down, okay, long division, and they got the value 909. So the closest answer to the option is obviously 911, so I have picked that as an answer. Okay, so they're asking me to estimate. Fine, makes sense. Let's try solving on our own also, so that we don't live in a fake hope. Let's see how long we take to solve this one simple calculation. It's not simple, it's very huge, but let's give it a try. There. So 10 raised to 8 upon 109678. So since this is 9, we can just round it off to what? 11,000? No, 1,10,000. So 10 raised to 8 upon 1,10,000. Okay. Now the numerator is bigger, we can cancel out the zeros. So there's 1 2 3 4 4 zeros, so left is positive. So 10 times 10 raised to 4, 11 into 10 raised to 4, this goes up, it becomes minus 4. So 10 raised to 4 upon 11. Now that we have 10 raised to 4 upon 11, there's nothing but 10,000 divided by 11. 2 3 4 10,000 divided by 11. We can just divide and see what value we get. So 11 times 9, we get 99, 1 and 10. Okay, instantly we are I don't think we have to take a 0 here. We can just take a 0. Okay, 11 times again 9 is 99. Okay, so the answer which I am getting is 909 something, which is obviously pretty close to 911.7 angstrom. So I think that will be our final answer, which we calculated at around 1 minute 40 seconds, I guess. Not bad. So we can basically use rounding off concept to find such weird calculations. So the first thing that should stuck in your mind is round it off to the closest value, which in this case was 1,10,000. Okay, so that was the first go at streaming, and in the coming days I'll try to solve more questions and try to complete entire chapters in one sitting so that I can actually complete my syllabus on time. Anyways, thank you for watching.